Hello and welcome back. In the previous videos, I've discussed the advancements that were made by several different physicists towards developing this photon theory of light, and how this photon theory of light was then later generalized to understand all sorts of different phenomena like particle wave duality and the Broglie waves, and then finally led to the development of Schrodinger's equation in quantum mechanics. And at the same time that people were studying the photon, in the early part of the 20th century, there was another problem that many physicists were focused on that also led to a lot of important developments in understanding quantum mechanics. And these problems mostly focused with understanding the nature of the atom. And I don't want to spend a whole lot of time talking about the history of the atom itself. So if you've taken a class in chemistry, then you've probably learned a lot about John Dalton and things like the law of multiple proportions, and how these ideas led to this theory that everything is made up of atoms. Instead, what I really want to focus on is the physics of the subatomic nature of the atom. So this idea that the atom is made up of these smaller parts, and how we actually describe these smaller parts inside the atom. And the first major advancement towards understanding the subatomic nature of the atom came in 1897, when J.J. Thomson discovered the electron, and this led to the first subatomic theory of the atom called the plum pudding model. And the basic idea behind the plum pudding model was that J.J. Thomson knew that the electron was a negatively charged particle. In fact, if you've taken my class, then you've worked through this problem, this experiment that J.J. Thomson had worked through, where he looked at the cyclotron radius of the electron and calculated from that the charge-to-mass ratio of the electron. So J.J. Thomson was well aware that the electron was a negatively charged particle. However, at the same time, people also knew that atoms were neutral, so atoms had no electrostatic charge. So in order to explain this difference, and also to explain why the atom was much, much bigger than the size of an electron, people proposed the first subatomic theory of atoms called the plum pudding model. And the basic idea behind this was that the atom was made up of this positively charged pudding, and then inside this positively charged pudding were these very small electrons. So it was basically like these little bits of fruit, these little electrons sitting inside this larger positively charged pudding. And in order to test this theory of the atom and to try to gain a little bit of a better understanding of what was actually going on inside the atom, Ernest Rutherford proposed this gold foil experiment that was actually performed by two of the students who were working in his lab, Marsden and Geiger. So the basic idea behind this experiment was that you could probe the subatomic nature of the atom and learn something about the subatomic nature of the atom by shooting these very, very small particles at atoms and watching what happens to those particles as they pass through these atoms. And so the way that they did this was that they used a radioactive source. And we haven't talked a whole lot about radioactive atoms, but certain types of radioactive atoms, when they decay, they'll emit different types of particles. And one type of particle which can be emitted during a radioactive decay is something called an alpha particle, which is basically just 2 protons and 2 neutrons. So it's the nucleus of a helium atom. And they directed these alpha particles at a very, very thin sheet of gold foil. So it's only just a few atoms thick. And they watched to see what happened to these alpha particles as they passed through this gold foil. And what Geiger had discovered was that some of these alpha particles, when they struck the gold foil, they were actually deflected backwards. And of course, this was a completely unexpected result, because at this time, everybody believed that these atoms were made up of this positively charged pudding. So if you shoot these somewhat massive and very fast-moving particles at this pudding, you would expect them to just pass straight through. It's kind of like if you shot a bullet at a brick of Jell-O pudding, then the bullet would just pass right through, right? You wouldn't expect the bullet to bounce off of a block of pudding. But that's exactly what they saw with these alpha particles. If the alpha particles were shot at the gold foil, some of the alpha particles were deflected back. And the only way that people could explain this result was if the atom had inside it a very, very massive particle. So the idea is that the alpha particle would strike these very massive particles and then basically bounce off of them. And because only a very small fraction of the alpha particles bounced off of the gold foil, Rutherford also knew that these very massive particles must be extremely small, because most of these alpha particles pass through the foil without ever colliding with this very massive particle. It's only a small fraction of the alpha particles that collide with them and bounce back. And this led to the next subatomic model of the atom, called the Planetary model. So the basic idea behind the Planetary model was that instead of this positive charge being spread out with this positively charged jello, Rutherford proposed that this positive charge was actually contained in this very massive yet very small positively charged particle called a nucleus, and that surrounding this nucleus were these electrons which orbited the nucleus in basically the same way that planets orbit the sun. Now, the Planetary model had two very significant problems with it. The first major problem with the Planetary model was that if these electrons are just orbiting the nucleus, like planets around the sun, then why can't the electrons just orbit at any radius? In other words, what's determining the size of the atoms? The second major problem, and this is a little bit more of a complicated type of a thing, but it turns out that whenever a charged particle accelerates, that charged particle will emit electromagnetic radiation. So we've talked about that a little bit when we first started talking about the black body problem. So remember, if you accelerate a charged particle, that particle will release electromagnetic radiation. So if I have these electrons and they're moving around in a circle, then these electrons are accelerating. There's this centripetal acceleration. And so these electrons should be constantly emitting light. And of course, this light will carry away with it some energy. So what will ultimately happen is that these electrons will be emitting light, and they'll slowly lose energy, and they'll slowly decay, and then eventually collide with the nucleus. And in fact, you can calculate the lifetime of something like a hydrogen atom, and you'll find that classically you would expect a hydrogen atom to only last for about 10 to the minus 11 seconds. So a hydrogen atom would just almost instantly disappear due to this effect. So how could we possibly explain what's going on inside this Planetary model? Well, the first major clue towards understanding the Planetary model of the atom came from yet another unsolved problem in physics. So in 1814, a very important physicist named Johann Fraunhofer, who made a lot of contributions towards understanding optics and interference, noticed that if you passed sunlight through a prism, instead of getting a complete spectrum from violet to red, there are actually these dark lines inside the spectrum. So there were these gaps, these very specific colors that were missing from the spectrum. And later on, physicists discovered that if you shine white light through any type of dilute gas, you will also find these gaps inside the spectrum, these very narrow lines that are missing. These are called spectral lines. And people discovered over time that the spectral lines that are missing are unique to the type of atoms that are inside this gas. So the spectral lines for hydrogen gas are different than the spectral lines for helium or oxygen or nitrogen or any other type of gas. And in fact, people can actually use these spectral lines to determine what types of atoms are present in a material. And this type of analysis is nowadays called spectroscopy. And for a very long time, physicists really didn't understand these spectral lines. So they saw that this was a really useful thing, and people were measuring these spectral lines, and they were all cataloged in these giant books, but people didn't really understand where these spectral lines were coming from. And the first major clue towards understanding the nature of these spectral lines came from a very unsuspecting place. In 1885, a schoolteacher named Johann Balmer discovered a pattern for the spectral lines for the hydrogen atom. And he decided to look at the hydrogen atom because this was the smallest atom, so he figured that this would give him the simplest formula. And he found that the wavelengths of these spectral lines was given by this formula right here. So 1 over the wavelength was equal to this constant called the Rydberg constant times 1 over 2 squared minus 1 over n squared, where n was an integer. And this constant here, this Rydberg constant, has a value of 1.1 times 10 to the 7 inverse meters. And Balmer had hypothesized that this 2 in here could actually be replaced with any other integer, except that now if you replace this 2 with a different integer, you would get wavelengths that would be outside the visible range of the spectrum. And in fact, as soon as Balmer published this formula, people started to use this formula to try to find new spectral lines, and they discovered all sorts of new spectral lines that obeyed this formula that they never even knew existed before. And this formula, when combined with the photon theory of light, was the big breakthrough that physicists finally needed to really understand what was going on inside the atom. So the next major model of the atom came from another physicist named Niels Bohr. And what Bohr realized was that what this formula is really telling you is it's saying that the electrons inside the atom can only absorb photons with very specific energies. Because remember that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. So if the electrons inside the atom can only absorb photons with very specific wavelengths, then what that means is that the electrons can only absorb photons with very specific energies. In fact, the energies of the photons are given by this formula, hcr times 1 over m squared minus 1 over n squared. And in particular, it was this difference between two basically identical formulas, this 1 over an integer squared minus a 1 over an integer squared, that really led Bohr to realize that, what this formula is really saying is that the electrons inside an atom can only have very specific amounts of energy, which are given by this formula, hcr divided by an integer squared. And that the electrons can only absorb a photon if the energy that's carried by that photon is equal to the difference between the energies of allowed states inside an atom. And the basic ideas behind the Bohr model is that the electrons inside an atom can only reside in very specific states with very specific amounts of energy, and that these very specific states, they're somehow very special. They don't obey the classical laws of physics. So even though this electron is presumed to still be orbiting the nucleus of the atom, the electron's not emitting light as it classically should. And that's why we call these states stationary states. And an electron inside an atom is only able to absorb a photon if the energy of this photon is equal to the energy difference between two stationary states. So because these electrons can only exist in the stationary states, the electron can only absorb a photon if the photon carries just the right amount of energy to move the electron from one stationary state to another stationary state. And this model, which was hypothesized by Niels Bohr, led to the next major advancement in understanding quantum mechanics. And this came nearly 10 years later in 1924. So in 1924, Louis de Broglie had hypothesized this idea of particle-wave duality. And we've actually talked about this earlier in this class. So this is the idea that even something like an electron can sometimes behave kind of like a wave. And so even an electron has a wavelength, and he said that this wavelength could be found by using the formula for the momentum of a photon and rewriting this to solve for the wavelength. So we would say that the wavelength of a de Broglie wave is equal to Planck's constant divided by the momentum of a particle. And the way that de Broglie had arrived at this idea was by studying the Bohr model of the atom. So going back to this formula that we have for the difference in the energy levels of the electrons inside a hydrogen atom, de Broglie was actually able to use this formula to calculate the energy levels that were allowed inside a hydrogen atom. So we can actually just look at this formula and we can see that the energy levels that are allowed are going to be equal to hcr times 1 over an integer squared. And so you can actually use this formula to calculate what radiuses are allowed for a Bohr atom. So there's this idea that you've got this nucleus here, and the electrons are only allowed to orbit the nucleus with very specific radiuses that are given by that formula. And what de Broglie had realized was that the diameter of these radiuses is exactly equal to an integer times the de Broglie wavelength for these electrons. So if we assume that these electrons have wavelengths which are given by this formula, then the diameter of these paths is always equal to an integer times this wavelength. So what this means is that you sort of get these standing waves that are going around in a circle. And so this is really where this idea of a de Broglie wave actually comes from. Now, over the years, physicists had come up with a number of formulas which you can use to calculate the energy levels of an electron inside different types of atoms. So for example, there's a formula which you can use to calculate the allowed energies of an electron inside a hydrogen atom. And then you can modify that formula to calculate the energies that are allowed for a single electron orbiting a different number of protons. And we're not going to spend any time in this class talking about these different types of formulas. That's not something that you're going to need to know for this class or for the AP exam. Instead, you're going to be given the allowed energy levels of the electrons inside an atom in terms of something called an energy level diagram. And basically what an energy level diagram is it's a graphical way of representing the energy levels that are allowed for an electron inside an atom. So you draw this vertical axis on which you plot the energy levels that are allowed for the electrons inside an atom. And one thing I should point out about these energy levels, so over here I have the energy level diagram for a hydrogen atom, and you can see that all of these energies are negative. And the reason for this, if we think about the energy of an electron inside the atom, well, we have the kinetic energy, 1/2 mv squared, and then you also have this electrostatic potential energy between the electron and the proton inside the atom. So that's going to be K Q1 Q2 over r squared. And because the electron and proton have opposite charges, this potential energy will always be negative. And if the kinetic energy of the electron was greater than the negative potential energy, then the electron would actually have enough energy to just leave the atom. So what these negative energies really mean is that that electron is bound to the atom. The electron doesn't have enough energy to actually escape the atom. Now, when we talk about the energy levels of an electron inside an atom, we say that when the electron moves from a lower energy state, like this n=1 state, up to a higher energy state, we say that the electron is excited. So we would say that the electron is excited from the n=1 to the n=2 state. And when the electron goes from a higher energy state to a lower energy state, we say that the electron decays to a lower energy state. Furthermore, we call the lowest energy level that the electron is allowed to have inside an atom the electron's ground state. And the highest energy level that an electron is allowed to have in any atom is this zero energy state. And this zero energy state occurs basically, if we look at this potential energy over here, so this will go to zero when the distance between the electron and the proton goes to infinity. And that's really what this zero energy state describes. It describes that state where the electron and the proton are completely separated from each other. And we say that whenever an electron moves from any of these states up to this zero energy state, this highest energy state, we say that the electron is ionized, or the atom has been ionized. And what that means is that the electron has been completely removed from the atom. And so these are all terms that you really need to know for this class in order to answer, basic problems that I could ask about the Bohr atom and the energy level diagrams. So for example, I could ask, well, how much energy is required to ionize an electron which starts out in the ground state? So you should be able to look at this and say, well, if it's starting out in the ground state, that means my electron's here, and the amount of energy I need to go and ionize the electron means the amount of energy I need to move the electron all the way up here. So that energy difference, that energy that I need to do that, is equal to 13.6 electron volts. So that's kind of a standard type of problem that you would need to be able to answer for this class. So let's take a look at a couple of examples. In this first example, we're given an energy level diagram for some hypothetical atom. and we're asked to calculate the wavelength of the absorption and emission spectra for this atom. So remember that the basic idea behind the Bohr atom is that an electron inside a Bohr atom will only absorb a photon if the energy that's carried by that photon is equal to the energy difference between two states inside the atom. So for example, looking at this atom here and just considering these three states, the n equals 1, n equals 2, and n equals 3 states, there are three possible transitions. The electron can go from the n equals 1 state up to the n equals 2 state. It can move from the n equals 1 all the way up to the n equals 3 state, or the electron can move from the n equals 2 up to the n equals 3 state. So these are all the transitions that correspond to the atom absorbing a photon, and therefore the electron gaining some energy. So looking at these three transitions, according to the Bohr model of the atom, the electrons inside this atom will only absorb a photon if the energy that's carried by that photon corresponds to these energy differences. So the energy difference between the n equals 1 and the n equals 2 state for this transition, the energy difference between the n equals 1 and n equals 3 state for this transition, and the energy difference between the n equals 2 and n equals 3 state for this transition. Now, since we're asked to calculate the wavelengths of the absorption spectra, we need to calculate the energy of a photon in terms of its wavelength. So remember that the energy of a photon is equal to Planck's constant times the frequency. So to write this in terms of the wavelength, we need to use the fact that the speed of light is equal to frequency times wavelength. So we can rewrite this and say that the frequency is equal to the speed of light divided by the wavelength, and plugging that into the formula for the energy of a photon, we see that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength of the photon. So again, going back to the n equals 1 to the n equals 2 transition, so if we move an electron from the n equals 1 up to the n equals 2 state, this corresponds to increasing the energy of this electron by 5 electron volts, because we're going to move the electron from a state where it has minus 9 electron volts up to a state where the electron has minus 4 electron volts. So this electron will gain 5 electron volts, and that energy that the electron gains comes from the photon that the electron absorbs. So that photon needs to carry 5 electron volts. So that photon has 5 electron volts, and that energy is equal to Planck's constant times the speed of light divided by its wavelength. So solving this for the wavelength of the photon, I see that's equal to Planck's constant times the speed of light divided by the energy. In this case, that energy is equal to 5 electron volts. And if I plug these numbers into a calculator, I can see that that wavelength will be equal to 248 nanometers. So this is the wavelength of light that you would need to excite an electron from the n equals 1 up to the n equals 2 state. So looking at the next transition, the n equals 1 to the n equals 3 state, so looking at that, we can see that that corresponds to increasing the potential energy, increasing the total energy of the electron by 8 electron volts, because we'll be moving the electron from a state where it has minus 9 electron volts up to a state where it has minus 1 electron volts. So the electron's energy will increase by 8 electron volts. So that means that the photon has to carry with it 8 electron volts of energy. So we can actually just use the same formula again. So the wavelength is going to be equal to Planck's constant times the speed of light, and this time divided by 8 electron volts. And if we plug this number into a calculator, we can see that this is equal to 155 nanometers. And then the final transition we have here, going from the n equals 2 up to the n equals 3 state. So again, we're just going to use the same formula. It's equal to Planck's constant times the speed of light, and the energy difference between these two states is equal to 3 electron volts. So we'll divide it by 3 electron volts. And if we plug these numbers into a calculator, we can see that this one is equal to 413 nanometers. So these are the 3 different wavelengths that the electrons inside this atom are allowed to absorb. So this gives us our absorption spectrum. Now the question also asked us to calculate the wavelengths for the emission spectra. So remember, the basic idea is that the atom will emit a photon when an electron moves from a higher energy state to a lower energy state. So if the electron goes from, say, n equals 3 down to the n equals 2, in this case, the electron is losing energy because it went from a state where it had minus 4 electron volts to a state where it has minus 4 electron volts. I'm sorry, minus 1 electron volt to a state where it has minus 4 electron volts. So it lost 3 electron volts of energy. And by conservation of energy, that means this electron has to emit a photon which will carry away with it that energy difference. So when the electron goes from the n equals 3 state down to the n equals 2 state, that electron will emit a photon that carries away 3 electron volts. But of course, that's just equal to 413 nanometers, the same wavelength of light that will excite the electron from the n equals 2 up to the n equals 3 state. So hopefully you can see that the wavelengths of light that will be emitted by the atom when the electrons decay to these lower energy states, they correspond to the same wavelengths of light that you would need to excite the electron between those same two states. So the absorption spectra is the exact same thing as the emission spectra. So the wavelengths of light that the atom will absorb are the same as the wavelengths of light that the atom will emit. So let's take a look at one more example. In this example, we're once again given an energy level diagram for a hypothetical atom. And this time we're only asked to calculate the wavelengths for the largest and smallest wavelength that the atom can absorb or emit. So once again, we could proceed with this problem exactly the same way that we did in the previous example. We could go through and calculate the wavelengths for all of the different transitions that are allowed for this atom. However, you can see right away that that's going to be a lot more difficult to do with this atom because we have a lot more energy levels for this atom. We've got 5 different energy levels, which means that the total number of transitions that we can have is equal to 4 plus 3 plus 2 plus 1. So there are 10 possible transitions that we can have for this atom. And it would take quite a while to go through and calculate them all one by one by one. And we don't have to do that. If we just think a little bit beforehand, we can realize that we can immediately figure out which transitions will have the largest and smallest wavelengths. So remember that the energy of a photon was equal to Planck's constant times the speed of light divided by the wavelength of the photon. So the smallest the smallest wavelength corresponds to the largest energy difference, and the largest wavelength corresponds to the smallest energy difference. So let me write this down. So the smallest wavelength means the largest energy difference. And if we look at this energy level diagram here, the largest energy level difference would correspond to moving an electron from the n equals 1 state all the way up to the n equals 5 state. Again, we're only considering the energy levels that I've included in here. So that would correspond to a photon which is carrying with it 14 electron volts of energy, the energy difference between these two levels. So again, we can calculate this wavelength the same way that we did in the previous example. So this will be equal to Planck's constant times the speed of light divided by this energy level difference between these two states. And if I plug these numbers into a calculator, I can see that this is going to be equal to, 89 nanometers. So that's the smallest wavelength that this atom can absorb. And similarly, if we have a very large wavelength, then that's going to correspond to a very small change in energy. So the largest wavelength means we're looking for the smallest change in energy between two energy levels. And we can see that the smallest energy difference corresponds to the energy difference between the n equals 4 and the n equals 5 transition. And that's going to be 2 electron volts. So once again, we'll use the same formula. The wavelength is equal to Planck's constant times the speed of light, and this time we're dividing it by 2 electron volts. And again, if we plug these numbers into a calculator, we can see that this wavelength is going to be equal to 620 nanometers. So that's the largest wavelength of light that this atom could absorb. And now there's one last topic that I'd like to talk about in this lecture, and that's the Pauli exclusion principle. So, while the Bohr model can explain why the electrons inside an atom can only exist in very specific states, and why an atom can only absorb or emit light with very specific wavelengths, it doesn't really explain where the chemical properties of the atom come from, or what happens if you have more than one electron inside an atom. And these properties are given by something called the Pauli exclusion principle. And if you've taken a class in chemistry, then you've probably heard of this before. And basically what the Pauli exclusion principle says is that you can have no more than one electron in any particular stationary state. And the reason that this gives rise to all of the different chemical properties of the atoms is that it turns out that all of the laws of physics are always trying to push everything into their lowest potential energy state. So, for example, let me just open up a blank screen here. So suppose I have an atom which has energy levels which look like this. And suppose this atom has 4 electrons. So according to the Pauli exclusion principle, all of my electrons have to go into different states. And because we're trying to minimize the energy, these electrons will go into the lowest energy states. So here's my energy, and you can see I've got other states up here, but there's this big gap between this state and the next state. Actually, let me put 5 electrons inside this atom. And now let's suppose I have another atom over here, and let's say it has energy levels which look like this. And let's say this atom over here only has 3 electrons inside of it. And then we've got some other energy levels up here. Well, we can see that if I move this electron from atom 1 over to atom 2, what will happen is I'll actually decrease the total potential energy, because this potential energy for this last electron inside atom 1, so we have atom 1 over here and we've got atom 2 over here, so this energy that we have for this last electron in atom 1 is a whole lot more than the energy that the electron would have if it moves over to atom 2. So this is actually where the chemical properties of atoms come from. It's because the forces of nature are always trying to minimize the potential energy in any system. So what will happen is that these atoms will actually share that electron, and that electron will mostly reside in this state. And the reason that these atoms will still be brought together is because of that electrostatic force. So if I give this atom 1 extra electron and I remove 1 electron from this atom, they'll have opposite charges, so they'll be attracted together by that electrostatic force. And you can actually derive basically all of the chemical properties of all of the elements in the periodic table just using Schrodinger's equation. So just using quantum mechanics, you can basically derive all of those basic ideas in chemistry. And so with this, I'd like to end our discussion on the Bohr model of the atom. And in the next video, we're going to begin talking about nuclear physics. So we'll talk about the strong nuclear force and the energy that can be released during nuclear reactions.